Now we shall discuss the last topic of this chapter, wave optics, which is known as polarization. Now, phenomena like interference and diffraction can be explained on the wave theory of light. But when you use wave theory, when you explain interference and diffraction, phenomena like interference and diffraction by using the wave theory, the next logical question will be, what kind of a wave is light? You know that there are two different kinds of waves. They are transverse and longitudinal. And the phenomenon polarization, beyond any doubt, clearly established that light is a transverse wave. So only by using the transverse nature of the light or the electromagnetic wave, we can explain the phenomenon called polarization. Now let us see what is meant by polarization. You know that light is an electromagnetic wave. It is a combination of electric field and magnetic field which are mutually perpendicular to each other, and both of them are perpendicular to the direction in which the wave is propagating. Now, even though light is a combination of electric field and magnetic field vectors, we will be interested only in the variations of the electric field vector. That is because all optical properties are determined by the electric field vector or variations in the electric field vector alone. So let us look at ordinary light. In ordinary light, the electric field vector has vibrations in all possible directions. So this is ordinary light in which the electric field vector is vibrating in all possible directions. Now we are familiar with vector algebra. We know that we have studied a topic called resolution of vectors, in which a vector lying in a plane, any plane, can be resolved along two mutually perpendicular directions. So if you use that concept here, we can resolve all these vectors which are lying along different directions along two mutually perpendicular directions. Here in this case, one parallel to the surface of the board and other one perpendicular to the surface of the board. The dot shows those vectors which are lying perpendicular to the plane of the board. So that is how we have resolved all these vectors which are lying along different directions. Let's see what happens when ordinary light is passed through a crystal called a tourmaline. So we will take a crystal called a tourmaline and let ordinary light pass through it. This crystal has an oscillographic axis, and we are now going to allow ordinary light to pass through it. So we have seen that in ordinary light, the vibrations of the electric field vector are, we have split them along two mutually perpendicular directions, one parallel to the plane of the board, other one perpendicular to the plane of the board. And this crystal has, as I told you, has a crystallographic axis. So when these vibrations pass through this crystal, the crystallographic axis of the crystal will act like a slit, and it will allow only those vibrations which are parallel to the slit to pass through it. So at the other end, what you get will be light in which the vibrations are confined to a single plane. The vibrations of the electric field vector are confined to a single plane at the other end, and these are the vibrations which were parallel to the crystallographic axis or the optic axis of the crystal. Now see, in the incoming light, vibrations were there on all possible directions, and all these vibrations had two components, one parallel to the plane of the board and the other one perpendicular to the plane of the board. And when we place the tourmaline crystal in front of such a light, incoming light, those vibrations which were parallel to the crystallographic axis of the crystal, and the axis of the crystal is now lying parallel to the plane of the board in our experiment. So what happens is, those vibrations which are parallel to the plane of the board are parallel to the optic axis of the crystal, and they will pass through the crystal. But the other kind of vibrations which are perpendicular to the plane of the board, which are also perpendicular to the optic axis of the crystal, they will be blocked by the crystal. They will be either blocked or removed by the crystal, and they will not be able to pass through it. So if the intensity of the incident light is I0, the intensity of the light that reaches at the other end will be I0 by 2. This is very simple because you know that intensity proportional to the square of the amplitude. So we have seen that half of the incoming vibrations are blocked by the crystal and only the remaining half is able to pass through the crystal. So this is the intensity of the transmitted light. Now let us see what happens if I rotate this crystal through 360 degree in steps of 90 degree. It's very simple, because if you rotate this crystal through 90 degree, or at first glance you may think that the intensity of the transmitted light will become 0, but that is not the case. Why? Because whatever be the position of the crystal, whatever be the position of the crystallographic axis of the crystal, there are vibrations which are always parallel to the crystallographic axis of the crystal at that position, because there are vibrations in all directions in the incoming light. Only for the simplicity of the treatment, we have split them along two mutually perpendicular directions. It does not mean that the vibrations are only parallel to the surface of the board or perpendicular to the plane of the surface of the board. The incoming light has vibrations of the electric field vector along all possible directions. So whatever be the position of the crystal, whatever be the direction in which its optic axis is aligned, there will be always vibrations which are able to pass through it. So the intensity of the transmitted light still will remain as I0 by 2. So if I rotate the crystal through 360 degree in steps of 90 degree, nothing will happen to the intensity of the transmitted light. Intensity of the transmitted light will always remain as I0 by 2 if I0 is the intensity of the incident light. Clear? Now let us see what will happen if I place two tourmaline crystals side by side, one adjacent to the other, and this is our incident light in which is unpolarized light. Vibrations are there in all possible directions, and we have them split them into two directions. Now you know that the light that emerging from the first crystal has vibrations confined to a single plane only, which is parallel to the crystallographic axis of the first crystal, which we call by the name P1. Now if the crystallographic axis of the two crystals remain parallel to each other, the transmitted light will be the same as that left the first crystal P1. Whatever be the intensity of the light that has passed through the crystal P1, the same intensity will be there when light passes through the crystal P2, because the crystallographic axis of the two crystals are parallel to each other. Now this is I0 by 2. If this is I0, this is I0 by 2, and this is also I0 by 2. Now if I rotate the second crystal, generally we call the first crystal as polarizer and the second one as analyzer. There is no clear-cut rule that this should be polarizer and this should be analyzer. You can interchange the crystals, and so there is no such tourmaline crystal which always act only as a polarizer or only as an analyzer. So now let us rotate the analyzer starting from 0 to 360 degree through steps of 90 degree. What will happen? It's now very much evident that as I rotate this crystal, the intensity gradually reduces from I0 by 2 to 0. Once the optic axis of the two crystals become perpendicular to each other, no light will be transmitted by the second crystal, and that is because the two axes are now mutually perpendicular. We say that the crystals are now crossed, the optic axes are now crossed with each other. So when we say that their optic axes are crossed, crystallographic axes are crossed, it means that the angle between them is 90 degree. So no light will pass through the second crystal. Now if I rotate again from 90 degree to 180 degree, the intensity will change from I0 by 2 to 0. So let us write it like here. We will write it here. 0 to 90, intensity varies from I0 by 2 to 0. Then 90 to 180, intensity varies from 0 to I0 by 2. Then 180 to 270, the intensity varies between I0 by 2 to 0. And finally from 270 to 360, the intensity varies between 0 and I0 by 2. So this is how the intensity vary when we rotate the crystal. The same is the situation if you keep the analyzer fixed and rotate the polarizer alone. The result will be the same. So if you allow light to pass through two crystals, and if you rotate one of the crystals by fixing the other one, the intensity will vary between 0 and I0 by 2 in one rotation from 0 to 90 degree. So here I have shown the complete change in the intensity with the angle of rotation. Now suppose we must have a general expression for this. Suppose I rotate the analyzer through an angle theta, then how will the intensity of the transmitted light vary? Then the formula for that is I equal to I dash cos square theta, and this is called Malus law. Here I dash is the intensity of the light that had fallen on the analyzer. Remember, polarized light falls on a tourmaline crystal, the intensity of the transmitted light will be I0 by 2. Whether you rotate it or not, the intensity will always remain the same as I0 by 2. But if you allow polarized light to fall on a tourmaline crystal and then you start rotating that crystal from 0 to 90 degree, then the intensity will vary according to the relation I equal to I dash cos square theta. Remember, here I dash is the intensity of the polarized light that is falling on the crystal, or here you have two crystals, so I dash is actually the intensity of the light that is falling on the second crystal, and in our arrangement it is I0 by 2, not I0. So this should be remembered very carefully. I dash is the intensity of the light, polarized light that is falling on the tourmaline crystal. Clear? This is called the Malus law, and this law is known as Malus law. So this law gives you an idea or a way to calculate the intensity of the light that is coming out of a crystal, a tourmaline or any such type of crystal, when polarized light falls on that crystal. Clear? Now let us see polarization by reflection. Suppose we have a reflecting surface here and light falls on the surface, unpolarized light falls on the surface. Part of it will be reflected and part of it will be transmitted. Now you know that when light is reflected from a surface like this, the reflected light will be polarized. We have unpolarized light falling on the reflecting surface. Vibrations are there in all possible directions, and when you allow this light to be reflected from the surface, we find that the reflected light is actually polarized. And the degree of polarization depends on the angle of incidence. The degree of, while most of the transmitted light remains unpolarized, so the reflected light remains polarized. And as we increase the angle of incidence, the degree of polarization also increases. And for a particular angle of incidence, the reflected light will be completely plane polarized. And that angle of incidence at which the reflected light becomes completely plane polarized is called polarizing angle, theta p. So polarizing angle is the angle of incidence at which the reflected light becomes completely plane polarized. Then the tangent of the polarizing angle will give you the refractive index of the medium. The tangent of the polarizing angle will give you the refractive index of the medium, and the refractive index of the medium, this is called this is called Brewsters law. You have studied this. This is called Brewsters law. So what is Brewsters law? Tangent of the polarizing angle gives the refractive index of the medium. Now, according to Cauchy's formula, which you have seen, mu equal to a plus b by lambda square plus etc. Other terms are there. We will limit our discussion only to the first two terms. A and b are known as Cauchy's constants. So mu is dependent on lambda. Mu has an inverse square dependence on lambda if you approximate to some extent. So mu depends on lambda and mu also depends on theta p. So theta, polarizing angle, depends on refractive index, and refractive index depends on wavelength. So you can say that since polarizing angle depends on refractive index and refractive index depends on wavelength, the polarizing angle will be different for different wavelengths. So theta p will be different for different lambda. Theta p will be different for different lambda. Polarizing angle depends on the wavelength of the light used. Clear? This is called the Brewster's law. So, and another point to remember here is that when the light is falling at an angle equal to polarizing angle on a reflecting surface, the reflected ray will be completely plane polarized, as I told you. Further, the reflected and the refracted rays will be mutually perpendicular. So they will be perpendicular to each other. The reflected ray and the refracted ray will be perpendicular to each other. Let us see what is meant by double refraction. Suppose I place a mark on a paper placed on a table, and if I place a calcite crystal on top of that mark, first I mark or make a mark on a piece of paper and place the paper on a table. Then over that mark I have placed a calcite crystal. So if I look through this calcite crystal, I will see two images of the mark that I have made. I have made only one mark, but if I look through the calcite crystal, I will be able to see two marks. And further, if I start rotating this calcite crystal, one of the images will remain stationary and the other one begins to rotate around the first one. And this phenomenon is called double refraction. This is called double refraction. And calcite is a doubly refracting crystal. So the image that remains stationary is called ordinary image, and the image that rotates around it is called extraordinary image. So this is the one that remains stationary is the ordinary image, and the one that rotates around it is called extraordinary image. Extraordinary image. Now we can see that refractive index of the material is different for both ordinary ray and extraordinary ray, because for both the ordinary ray and extraordinary ray the angle of incidence will be the same, because only one light ray is entering into the medium. But inside the crystal, the ordinary ray and extraordinary ray is the one which is responsible for producing the ordinary image, and extraordinary ray is the one that is responsible for producing the extraordinary image. So they will travel with the different speeds. So the refractive index of the crystal for ordinary ray and extraordinary ray will be different. Some crystals, the refractive index for ordinary ray will be greater than that for extraordinary ray, and for some other crystals it will be the opposite. That depends on the nature of the crystal. So this phenomenon is known as double refraction. Now let us see an instrument or a crystal that works on the principle of double refraction, and that is called a nickel prism. So this is our nickel prism. A calcite crystal is taken, it is cut diagonally, and the two pieces are joined by a paste called Canada balsam. Canada balsam. So using a paste called Canada balsam, we have joined the two pieces together. You know that just now I have told you that calcite is a doubly refracting crystal. So I cut the calcite crystal along the cut it diagonally and join the two pieces by using a paste called Canada balsam. The Canada balsam has a different refractive index than calcite. So when light enters into this, it will split into two rays, ordinary and extraordinary rays. And when they passes through the Canada balsam layer, the ordinary light will be removed by the Canada balsam layer either by absorption or by reflection, and it will allow only the extraordinary ray to pass through it. So the light that you get at the other side of the prism will be completely plane polarized. So the nickel prism is used for producing polarized light. Nickel prism. This is used for producing polarized light. So using the Canada balsam layer, you remove either the extraordinary ray or the ordinary ray. One of them can be removed. So after removing one of the rays, at the other end you will get polarized light, which contains vibrations which are confined only to a single plane. And for that purpose we use nickel prism. And one more property is used here, which is the property of selective absorption. You see, when light enters into the calcite crystal, it will split into ordinary ray and extraordinary ray, and one of them will be removed by the Canada balsam layer. So it is a kind of selective absorption. So here what the Canada balsam layer had done is to remove one of the rays from the incident rays, and that is called a selective absorption, and this phenomenon is called dichroism. So this is called dichroism. This phenomenon is known as dichroism. So dichroism is basically selective absorption. Clear? So this nickel prism is used for producing plane polarized light. Finally, we will have a small discussion on optical activity. Optical activity is something which you have studied in your chemistry theory. Optical activity. And what is meant by optical activity? Optical activity is the property by which certain substances rotate the plane of vibration as polarized light is passed through them. So when polarized light is passed through certain substances, these substances show the property to rotate the plane of vibration as the light passes through them. This is called optical activity, and the substances which are capable of doing this are called optically active. Now we have a formula. If theta is the angle through which the plane of vibration is rotated, then theta proportional to L, length of the medium, and theta proportional to the concentration of the medium. Then we will write theta equal to a constant S into LC, and S is equal to theta by LC. Here S is called specific rotatory power. Theta is the angle through which the plane of vibration is rotated, L is the length of the medium, C is the concentration of the medium. Then specific rotatory power is given by theta by LC. Now you know that for a given length of the optically active medium, theta is proportional to C, concentration. But concentration is proportional to refractive index and N proportional to 1 by lambda square if you approximate Cauchy's formula. So theta, for a given length of the optically active medium, theta is proportional to concentration, concentration proportional to refractive index, and refractive index is inversely proportional to 1 by lambda square. So we can say if you will keep the length of the optically active medium constant, the degree of rotation will be different when we change the wavelength of the medium. As the wavelength of the medium, light changes, the degree of rotation will also change for a given length of the optically active medium. Similarly, for a given concentration, the degree of rotation increases with the increase in the length of the medium. For a given concentration, the angle through which the vibration is the plane of vibration is rotated is directly proportional to the length of the medium. So as the length of the medium increases, the degree of rotation also increases.